everybody, my name is Joanna Liu, and I'm going to be going through security networking challenges in first-person shooting games. So I'm going to walk you through the technical backbone of modern first-person shooting games, specifically how networking, distributed systems, and security architectures come together to support real-time competitive play. First-person shooting games are a perfect case study because they push the limits of low latency networking and are constantly under attack from cheaters and adversaries. So there's going to be some videos in here, and hopefully I could talk fast enough to keep up with the animations and videos that I put in. So this is just a video of, that's really quick, but just a video of like first person shooting, all the different angles. Don't worry, I'll explain it. So first person shooting games are unlike almost any other online application. So they require a sub 100 millisecond responsiveness, which means it's high frequency state updates, global scalability. At the very same time, they're one of the most targeted industries for DDoS attacks and client-side cheating. That's not good. So this combination, real-time networking plus adversarial pressures, make first-person shooting games an ideal environment to study real-time distributed systems and cybersecurity architectures. So modern FPS games rely on the authoritative server model. So this means the server, not the client, decides what actually happens in real time. This prevents players from modifying their client to cheat. For example, in Valorant, the server validates movement, recoil, shooting, projectile path, the hit registration. Even if it is a compromised client sends a fake data, the server will reject it. So this model is more expensive to upkeep, but it's the only way to maintain that competitive integrity. So let's see if I can keep up with this one. Lag compensation is one of the hardest challenges in FPS netcode. So servers use prediction, interpolation, and server-side rewind to reconstruct past game states. For example, Valorant rewinds up to 140 milliseconds to determine whether a shot should count. So these systems keep gameplay fair even when the players have different latencies, but they also create opportunities for abuse if players intentionally manipulate their connection. So let's say a player shoots an enemy at a client time for about 1,000 milliseconds to the firing information is packed into a user command and sent, as you can see, to the server while the packet is on its way through the network. The server continues to simulate the word, and the target might have moved to a different position by now. And the player's input arrives at a client time of 1,100 milliseconds, and the server would not register the hit, even though the player is aimed exactly at the target. The solution to this is a bit complex. For every tick, the server is creating a whole new environment state and should now save the last couple of seconds worth of states to see now that we can do this when a player shoots and the server receives the request, rewinds all the players back to where they were at the same spot in that point in time. So when the client performed the shot, essentially traveling back in time to see whether the player would have hit them or not after the shot, the server moves all the objects to where they were before this happens in one tick. So none of the players can see this happening. Clearly I can't talk fast enough, so let's see about links. So tick rate is how often the server updates the game world. It's a world and its environment. So a 128 tick server updates twice as often as a 64 tick server, which improves responsiveness and hit accuracy. So in Counter-Strike 2, introduce a sub-tick, which is a system that interpolates between ticks, reducing the latency even further, which gives you a really nice gameplay and environment. So the trade-off is, like I said before, cost. So the higher the tick rate, it requires more CPU, which cycles and more bandwidth across thousands of servers. So let's go to the next part. There's two versions. One being the client, which would be the version that is distributed out to the players, and to the other, which was a headless server version that would be responsible for managing all the multiplayer aspects. So I was going through here and showing you that this is an editing tool, is what allows a seamless switch between the two to perform the functions regarding the server and the client, and to be able to move some players around in the scene to have them update for all players. It's nice, but comes the first problem where you can see that sending any data over the network takes time for the data to get from point A to point B and must travel down miles of cables to get to their called network latency. And it creates multitude of issues. The first problem you see was where the player moves from when the key W on their input over the server. So the server will move the player for us and send back a new position. But if we were to delay this action, it would feel kind of sluggish. It would not make the game playable. It would make the game unplayable. So in modern first-person shooting games, it uses an authoritative server model, which, as I said in the first slide, it's the server, not the client. So there's obviously more than just players. There's objects in the game as well, all on the network needing to be synchronized. So they're saved onto the world state position, rotation, health, and inventory data. It was all kind of shown in the, I'm clearly talking too slow. And they're all packaged into a network packet and sent over to the client, where it's essentially just binary messages, which you saw a little bit earlier. And they transverse this internet, they transverse over the internet, and they're received by the client. And this whole process of packaging up the state of the world and just sending it to the clients happens at a frequent set by the developers, which is known as a server tick rate. That some tick rates vary between as low as 10 ticks and as high as 128 ticks. The tick rate state denotes how frequently the state of the world can be sent and received. I'll just play it again. So having a background in networking, how is it possible to fit all of this data about the world into one packet, compressing the packet with like a lightweight compression algorithm? That's what I was talking about. And is not enough to trim the packet down to a small enough size, though instead of us solely compressing byte, we can calculate the difference between two world states to only one new data packet called delta. Just kind of like the change of it. And compressing this works by first tagging all the world states into one ID. So as you can see, that's basically that slide. Let's go to the next one. When a client receives one of those world states, it makes sure to tell the server the most recent world state ID generally. Let's see. Okay. When the client receives one of these states, it makes sure to tell the server the most recent received world state. Generally, this is done by adding it to the client's input messages so that can track the received states and the ones that need to be sent over. So this minimizes the amount of data needed to be sent over. So there's lag compensation is one of the hardest engineering challenges in first-person shooting netcode. So servers use prediction, interpolation, and server-side rewind to reconstruct past game states. So yeah, that's got it. So why don't we just move players on their own and tell the server where we are in the world, so the server can just tell the other clients, well, because of cheaters. Essentially, you always have to assume that any player could just be trying to cheat, and must mitigate it the best that we can. In this case would be to prevent things like teleportation or speed hacks, or that the client could just tell the server they're moving faster, and they actually are, instead of relying completely on the server to set out players' position. So in first-person shooting games, they face two major categories of threats. Clearly the video ended, so I'm going to keep talking. Network level and client side. Network level threats include DDoS attacks, packet injection, and session hijacking. So in client side, threats include aimbots, wall hacks, trigger bots, kernel level cheats. These are all on the kernel level. So kernel level cheats are essentially dangerous because they operate at the same privilege level as the operating system. These threats aren't theoretical, so professional Rainbow Six Siege players have been DDoS during tournaments. Warzone has struggled with kernel level cheats that bypass traditional anti-cheat codes. And Counter-Strike 2 has had exploits that manipulate packet timing, like to abuse and its sub-tick system. So these are all huge things that could really mess a tournament, mess up a game, mess up whatever is happening on gameplay. Clearly, I don't play enough games, so you're going to listen to me talk about it. We can instead predict where the players should be locally first, meaning when we press a key, it will immediately be updated on your screen, which we put our input. The server will be then performing the calculations regarding the movement and send our actual position back when the event receives the position from the server. The client will then compare the two, and if they match, continue as normal. If the difference between the prediction and the actual position is greater than some threshold, you'd have to assume that the client's position is wrong and force the client to be in the correct position. This is done through a direct setting of the position, instead taking the last position the client has verified to be correct. And then I'm going to replay this again. If it's and all our input since the verification hopefully to give the correct result this time as part of the call reconciliation, which is as seen as a rubber band. So now that the server has all this correct player positioning going on, and the hack client has tried to modify this, but it will not be reflected into real play. So there's obviously more than just players. To counter these threats, the first-person shooting games are using multi-layer anti-cheating code. So kernel-level anti-cheat tools like Riot Vanguard detect unauthorized drivers and memory manipulation. So server-side validation ensures players perform impossible actions. They can't perform impossible actions, I'm sorry. Machine learning models analyze aiming patterns and reaction time to detect subtle cheating. And integrity verification ensures the game client has been modified. DDoS mitigation is equally important. So games rely on Anycast, routing through providers like Cloudflare and Akami. So traffic is completely scrubbed at the global scale. And it's all these cloud points of presence before reaching the game servers. So modern games also mask players' IPs, which is very good because by doing so, the player's IP addressing and routing traffic is through relay servers, which protects the high-profile players from targeted attacks. And that is the end of my presentation. Thank you so much for listening to me, and hopefully I can talk a little faster the next time that I do this. But I really appreciate everybody listening to my presentation, and hopefully the visuals helped a little bit better with understanding tick rates, the network architecture, and the cybersecurity behind what makes first-person shooting games so very important to protect, prevent, and protect in our future of modern first-person shooting games in any world that we are in. Thank you so much.